Hi, welcome back to the breadboard, and finally another episode for our power project, power supply for the bench, for the young enthusiast or professional alike. In previous videos of the power supply project, we have looked at the various components that make up the analog side of the power supply, using a couple of potentiometers to adjust current and volts. In this video, what I'm going to do is go to the other end and look at how we can automate the power supply, or more specifically, how we can use a microcontroller to use some modern displays like the one you can see here and some rotary encoders to control the power supply. And what I've used here is a Nextion 7-inch display that you can get from IT Studio, a small downloadable design tool that lets you set the layouts, and an Arduino. And the other things, I'll show you a closer view of everything in just a moment. The only other thing I've got on here is a TMP275 temperature sensor as well, because you would use something like that to measure the temperature of a heatsink in a power supply to be able to control it. So I started this project using an Arduino Uno, and if you look back at the video I did a week or so ago regarding the Nextion displays, you'll see that I was using an Uno to talk to the displays there. Now, the problem I had with the Arduino Uno is not that I ran out of program space, but because I was having so many parameters and strings and things that I was playing with for the display, I ran out of RAM and was starting to get some issues. So I had to switch to using an Arduino Mega for this project. There's nothing wrong with the Uno for simpler projects, and I'm still, even with the Mega, not using any more RAM than an Uno has available. I think I'm only up to about 25K, and the Uno has about 32K. Work RAM for variables and everything else, though, I'm up to about 3K. With the Mega, it's got 8K in it, so I got plenty of headroom. But in the Uno, it's only got 2K, so I'm already way above that. But anyway, this is a display that I came up with. It's not quite it's not the same as the one that you had seen before. And what I've got here, as you can see, is I have let me find a pointer here. I have my volts with a set point, and we'll have a closer look at this as well. I've got amps with set point. I've got power being calculated simply amps times volts. Watt hours accumulating in the bottom, and then I've got temperature over on the right hand side here. The buttons underneath are for indicators for things like constant voltage or constant current, setting the volts. So if I just simply press these, you'll see it comes up with a set volts display. So I can put in a value here, say 12.5 volts, press the OK, and now the set point here is set to 12.5. I can do the same for the amps, or I could say put in 4.2 amps as a limit, and now my limit for the amps is set to 4.2. I have a graph down here that I can turn on and off tracking of each of these displays, the main elements, so the volts, the amps, the power, and the temperature. I can just turn them off by hitting this little graph button on the side, and that will shut them all off. And I can just turn one on, and it'll keep going. Now, I have a couple of things I haven't figured out how to do yet. For instance, when I've turned one on, the rest of the display is still showing everything else, and what I need to do is refresh the graph. So because I'm not keeping the history of the graph on the Arduino Mega, which I could do, when I switch off one of the traces, it simply stops sending data to it right now. As I say, this is an early prototype of what I want to do for the Arduino powered power supply, assuming I stay with the Arduino. I think I do like the display, but I may have some more work to do with the things like the graphing and stuff, and maybe for the initial one I won't use the graph, or I'll put it onto a separate page so that you can go view it if you want to, or something like that, and have more use of variables in the Mega to store the traces that I want to keep track of. The other one I've got here, the other button on here, is an output button, which allows me to turn on and off an equivalent of an output relay. I have an LED connected to it right now, but that could easily be anything that you like. If you can power an LED, then you can drive pretty much anything as long as you give it the right interfacing. The temperature has an alert button, which is not coded in yet, and it has a graphing button. the power has the ability, the accumulator here, for the watt hours. I can clear that by just pressing a button and it would restart again. So if you're monitoring, say, a battery for discharge current, this right now, the two analog inputs, if you set them up for the right scale, right now they're assuming 0 to 5 volts in. If you used a shunt resistor and measuring the volts through appropriate voltage dividers, etc., you could actually monitor a battery discharge characteristics and accumulate the power that was actually being drawn out of the battery as well as the instantaneous power quite easily. So that will be something you could also use this kind of display for. In our case, we're working towards hooking this up with our power supply. I don't have any D to A converters connected yet, so when I change the set points, nothing actually happens except that it remembers it. The analog actual readings, though, for the analog volts and amps are actually connected to the analog to digital converter inputs. That's why they're floating around a little bit, because there's nothing actually connected to those analog inputs of the Arduino Mega. The temperature is real. It's measuring the ambient temperature of the room. And I also have a couple of rotary encoder switches, which I will just take go to a wider angle view so that you can see. Okay, so now you can see everything that's involved. I think you can still see the display clear enough, hopefully, to see what I'm doing. I have two rotary encoders hooked up to the Arduino Mega, using an interrupt scanning every millisecond to see if anything's happened with them. And I have an LED hooked up to allow us to see the equivalent state of the output. I've just bent it so you can see it easier from the camera. And if I press on the output button, you'll see I can turn that LED on right here and off, on, off. When I move one of the rotary encoders, I've got one for volts. It's right now only moving about 10 millivolts a step, and the other one is moving the amps about 10 milliamps a step. I do have a library in there which supports acceleration. If I just zoom in a little bit, so you see now as I rotate this pot, the volts display here is actually cranking up. Sorry, the set point for the volts is cranking up as well. Now if I turn this continuously, it will accelerate. See, it's going up. All right, see, it's now going up a lot faster because I'm continually turning this. If I get to 30, it will just stop there. Now, if I want to go to a specific voltage rather than doing that, that's great for fine adjustments. I can just hit set and go to, say, 25, press OK, and then I could just crank it, tweak it a little bit from there. Now, as I said, the output is not reflecting the input right now. I haven't got the whole loop closed off. For amps, I can go up to 5 amps. I've set a limit on that in the code. And when I get to 5, it just simply stops, as you can see there. And if I crank it back down again, all right, it will come down, but it won't go above the 5 amps. Now, I've got a routine in here that does a float to ASCII conversion, and it's not 100% perfect. It's a little bit of a shortcut one, so it does get sometimes the finer digits of converting these numbers wrong from what's actually stored in memory. But that's nothing to do with the display or the basic functionality. There's just that one functional routine that's wrong. And you can see here I can tweak these when I get up to 30 volts. On the volts, it will also limit. I can't go below 0, and I can't go above 30. This touchscreen works very nicely with this pen. So if I put 29.5 in there, and then try and go up from there, right, it will not let me go above 30. It just stops there no matter how much I turn, but I can come back down from that. And if I go down to 0, so let me just put 0.1, right, and I try and go down from there, it'll get to 0 and just stop at 0 as well. Which is just what you want for adjusting. Of course, if you have a power supply that goes plus and minus, then that would change things. So let me just reset the Arduino Mega here a second. All right, I have it coming up with a nice little splash screen for the breadboard, of course. And then the default condition is all of the tracing is off. And if I just put my finger on the temperature probe, I'm just holding it on here right now, so it'll take about 10 seconds before it will get that new reading. Temperature normally doesn't change. I have parameters in here that will allow you to change how often it reads the sensors and updates the displays, so you can just tweak it. I have the update set to 10 seconds, but it's actually reading the display every second at the moment, but you can, so you could, if you wanted to, add some averaging algorithms and things like that in there. You can see here that it's slowly updating, and you see that graph creeping up there for the temperature, and that's the only one I'm graphing right now. So if I let go, you'll see it will start coming down. Now I can add volts to the graph and amps. Now the problem is when I turn the temperature off, this is just an issue with the Nextion here. The current display doesn't clear, and it doesn't move along with anything else being added either. So it might be better in this case to have separate displays for each of these parameters rather than having them all on one. The other thing about this is that I'm displaying it on here, but because you're using an Arduino Mega, there's plenty of room here to add some networking as well to the Mega, or even through the serial port to a PC, so that you could log the data up to a PC and have it save it to a CSV file or something like that. And if you're using the power system, because you can see here that what we're designing ultimately is a power system that's going to have a power supply, DC load, a constant current source, and things like that, and also be able to perform some more advanced functions like battery discharge, battery charge cycles, etc. It will be good to be able to have the data being sent to a PC or something more intelligent. It might be a Raspberry Pi, whatever, so that you could actually do a complete charge-discharge cycle, measure the capacity and characteristics of a battery, etc., etc. That's something, as we go along, I want to look at. And the Mega may be ideal for the local controller, but we might look at launch pads and things like that. I will experiment with a few different things as we go on. But I will be having an interface, whether that be by a Wi-Fi, Ethernet, or via the USB, so that I can send the data for logging purposes up to a PC. And maybe we'll even implement a SCPI interface, which would make it industry standard with things like LabVIEW and stuff like that. Anyway, I just wanted to introduce you to what I was doing here. This is the display, of course, that is going to be used, or something like this at the end of the day, for the power supply project. And the next thing we're going to have to do is add some better interfacing to the PC, but more importantly, of course, adding D to A converters and a higher resolution A to D converter, so that we can read the actual voltages and things from the power supply, high-powered side of the system. And that will be in the next power supply video. Is we'll look at some of the ADC and D to A options, talk a little bit about resolution and what we want to do. Now, in the meantime, if you have any suggestions for improving the display, I will be happy to hear it. What we're going to do now is quickly go to the PC and have a look at the design tool and also the Arduino code that I am using to drive this. And all of this code and everything else I will make available to you on my GitHub channel. So stay tuned. So let's go get to the PC and see what is in the code and what is in the designer for the Nextion display. I actually designed the layout in here first, just dragged a few graphic pieces in, like these LCD looking areas for the text to go into, and set points and things. The buttons I found Googling around, dragged in my logo, of course, and just set up a few things. Now what you'll see here is that I have three separate displays. So the first one is basically with everything off, or inactive state, so all the buttons have no rings around them except for the output one, which is green, indicating that it is off. The next display, as you can see here, has all of the buttons active, and the output one is now red to indicate that it is on. I think I should probably change that to be a much more obvious, I think, than just that. And then the last one, this is something I'm going to get to in a minute, but this one includes the numeric input for setting the set points and things like that through this numeric keypad. Now, this is not part of my initial use case that I was using, because I was having this display coming up as a separate page, so all of this background stuff was not there. But there was something that I discovered, and I have a little video just demonstrating this that I can show you right now, and then we'll get back to continuing of what I changed to make it better. This is the Nextion editor for the Power Supply project, and one of the things I've just discovered here is right now I have a whole bunch of scripts on these save and cancel that basically closes all of the buttons and hides them because the display is quite slow bringing up another page, and when I go back to the first page it resets all of the controls. So what I've done is I've made them all one page, and then I've overlaid the keypad on top of that first page, and I just hide everything. But hiding everything in a script where I just say visible cancel equals 0, save equals 0, B0, B1, B2, etc., is very slow, as I can demonstrate right here. So here is the screen, the Nextion editor, and if I just bring it into better view there. Alright, so when I say set, it comes up very quickly and I can put in the data, but look at what happens when I try and save it. And that's even in the debugger. It does the same thing on the actual display. So if I say set, it comes up pretty instantly. If I close, do that again, I'll see if I can press it really quickly. Right, didn't miss anything, so it enables it very quickly when it's drawing. But when it's clearing it, probably because it's got to redraw the background, it has a much harder time doing that. So I'm just going to try something to see if I can speed it up. And what I think you can do, there is a command called viz255, 1. And if you say 255 with the visibility, it means it's all of the controls for the current page. And I know that they enable quickly enough, but they don't disable very quickly. So I'm going to try using visibility equals 0 and then just enable the ones that I have. So let me just change the settings for that, and I'll get back to you and let you know how well it works. So as you can see in that little video, the rendering time as it's clearing this numeric keypad off the screen was quite slow. Now the same thing happened when I was doing it either from the Arduino or from scripting within the actual screen itself. And the issue is definitely because it is having to redraw the background as things slowly get turned off. The turn off is quite quick. I think it's just the redrawing is slow. Obviously when you're actually adding something to the screen, it doesn't have to check the background and recover it. It just has to draw the new graphics straight on the screen, and I don't think it cares what was there before. Now what I've done, I can't demonstrate it straight from the designer right now because I've actually got the Arduino doing the work, and you saw on the initial display that I showed you at the beginning of this posting that it actually is working quite well now. And so the viz255, 0 works very well because it clears everything off in one go, and it just rewrites the background, and then I just turn everything on that I need for that current screen setting. It would be a lot easier if the page 1 and page 2 would work better than they currently do. What I found was happening is that when I turn on the second page, which was containing the numeric keypad and its own display, everything in the first page, page 0, just stopped. I couldn't write to them, I couldn't change the content. So if I was busy, maybe I'd had it running for an hour or two and adding charts from a battery discharge, the minute I switched the page up to maybe change your voltage or look at something else or maybe change the threshold, and then switch back to page 0, that graph would be completely emptied, which really was a little bit useless, to be honest. That's not, what you would want to do. And the only way around that I can think of right now would be to store all the data points for the graph in the Arduino or whatever other controller you happen to be using, and then when you know that you switch pages, you would then rewrite all the current trend data back to the graph. Which of course would be a little bit time consuming. You'd want to increase the baud rate from 9600 up to 115K2 for sure in that scenario. Obviously remembering the state of all of the buttons and everything is easy enough because they're just two-state booleans and things, and to redraw them would be pretty quick. To lose the data and have, to store the chart data and things would be a bit of a pain. Also, if I've got certain volts and amps on these displays, when it reinitializes, it also writes back the default values and has to wait for the next refresh cycle to update those. Now that's easy surmountable. As soon as you select page 0, you can just immediately do a display update, and you'll see that in my functionality when we look at the code to rewrite these almost instantly, which is okay. But obviously the biggest issue is the chart data that would normally sit behind this numeric keypad. If we were charting, losing that and trying to store that in a microcontroller, you suddenly increase your RAM requirements by at least a couple of K. So that's not very desirable. So I will be speaking to Nextion about fixing that. But for now, the way that I'm doing this, just by changing the visibility of the controls, I can still write to them, and that includes the trending. So even though this way of designing, of having the overlays all on the same page, is more complex because you cannot see what is being what's happening with the ones underneath. So if I bring up the actual, this is the PowerPoint that we're looking at right here, where I designed these pages. But if I bring up the actual Nextion editor, which is here, all right, this is the main page, and you can see here's the trend area. And then when I bring up, this is the earlier design, and then I had this page, which was supposed to just bring up this area here. I had scaled it to just be this, and it would sit on top. And that's great, but trying to access the hidden page now, or the one that's on the lower layer, can't be done while this is happening. So it was proving problematic. So that's a little bit of a firmware update that I think Nextion will have to do for their displays. But this is not insurmountable. Like I said, designing for page 0, you can see all the controls. Then you got I've got the graphic which I'm using for the other states with the crop areas for each of these controls. And then I've got my numeric keypad here. Now what I've done is I've set up a separate project, which is the way that I've got the system running right now. So I'm just going to open that and show you the changes. So you can see how easy you can identify each of the controls here. So this one is got pretty much the exact same set of controls, but you can see here there is only one page. And the graphical display for the keypad is smack in the middle of everything, so I can't get access easily to the controls that are underneath here. So I laid out the first area, and then I put the second area on top. And even things like the page load of here, I've added a script. So the first thing it does when it comes up, you can see at the bottom here, is it sets the keypad pick, which is this area here. This is the size of this whole keypad area. I've set it to picture 0, which is the background, which means it effectively hides the stainless steel looking buttons and texture of this area. I then set the visibility to 0 for all of those particular items that I don't want to be seen. Now that, because it's on initialization, happens very, very quickly because it hasn't been drawn yet. It's the pre-initialize event. So it does all that, and then it enables the screen. And that hides it right off the bat. And then after that, I programmatically will disable everything and then turn on the controls that I want to use. And that seems to work very, very quickly, as you saw in the beginning of the video where I was showing you it operating. So I've got my 3 graphics. I've got my splash logo, which also comes up under program control from the Arduino. And you saw that again. I'll reinsert the video, or that piece of the video right here, so you can see it again. So that on initialization, the Arduino says, hey, it's the breadboard, blah, 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 and then lets that splash screen disappear, and then it shows the normal operating screen, which is exactly what we want. It's just a little bit more difficult to be designing this. So let's get back now and have a look at the Arduino code. So here's the code. Currently, it does not actually have any external components except for the TMP275 temperature sensor. Everything else is just using either just stored in a variable, or is, in the case of the analog input channel, it's just reading from the ADC 0 and 1. So what we have here, if you saw my previous video on a TI Tuesday where I was looking at the TMP275s and things like that, then you'll know a little bit about how I was communicating with it using I2C bus. I've taken that and extended it and put a new display on it, which I've just shown you. for driving my power supply project. So what are the changes that I've done here? Well, we've got the wire interface for I2C. We've got the Nextion H being included, which gives us access to the Nextion libraries. And I've also included the click encoder because I've put two rotary encoders, as you saw, onto the inputs of the Arduino Mega as well. Timer 1 is just so that I can have a scheduled process polling the click encoders so that basically it's being read every millisecond to see if the rotary encoder has been turned or if the button's been pressed and things like that. Now, the Nextion, I'm not going to go into a whole design aspect of the Nextion here. Some of this will be familiar when I actually did a review of the Nextion displays, and that's in one of my previous videos just recently. I'll provide a link to that in the post when I put this up. But basically these are all the declarations for all of the elements on the Nextion display. I originally had 2 pages as I just described. So page 1 is currently not being used, only page 0. And all of these elements are all of the ones that I actively use to either talk to or read from. All right, so that's all these. Scrolling down here, we have a couple of buffers for receiving and manipulating data that's coming from the Nextion and other areas. Declaring all of the items that would be touch enabled or that might be sending responses back to the Arduino from the Nextion when I communicate with it. So for the power supply itself, here's all the variables that I am using. Maximum, minimum volts, maximum, minimum amps, the current voltage and current setting, the actual measured amps and volts, and the actual watts and watt hour values. A little boolean just indicates whether I've currently got the keypad displayed or not, and then 4 booleans to control whether I am graphing each of the various measured elements, the volts, the amps, the watts, and the temperature. I've separated out the timers for various functions into independent timers so they can be tweaked on their own. A couple of initializers that have been enabled for the encoders. These are the rotary encoders, and I'll provide a link to the kind that I have. Timer initialization. This event, the timer ISR, is going to be called every single millisecond, and then the 2 encoders I have, one for volts, one for amps, will be scanned to see if the buttons have been pressed, whether they've been turned, and things like that. The Nextion init, NAX init, is the same initialization as I had pretty much earlier for the previous videos. I've just moved it into a separate function just to keep coding a little bit easier. Before I initialize the callbacks, I show my splash screen for 5 seconds. Initialize the volts and amps on power up to be 0 and 0 for both of those. And that's pretty much done the setup. As you can see here now, the loop function is much, much simpler. Every iteration through the loop, I called next loop, which is actually a scan for the Nextion displays to see if any messages have come in from the display on the serial port. And I call get encoder values, which will go and see if it's time yet to scan the to go and see if any of the encoder buttons or rotations have occurred since the last time we were through here. And we can check this every single time so we don't miss an event. But remember, in the background, every millisecond, it's actually monitoring the physical switches. All we're doing here is we're going to look to see if anything has actually changed. So if we go down and look at the first part here, this is all of the encoder functions. I've just put a comment in the beginning and I've kept them all together to make reviewing easier. So this is the init encoders. So I call the initialization routine, give it the pins for the data. I give it the pin for the button, which is, so we've got 2 and 3 for data. So that's A and B on a rotary encoder. I've got the button input, and then the 4 means that it's 4 clicks for one position on the rotary encoder. We initialize the timer for 1000 microseconds, basically 1 millisecond, and we set it going. And a couple of another local variables. All right, so the next bit here, the next function is actually to do with reading the encoders. And I took the encoder library and one of the examples and I adapted it for my own use. So we basically read the voltage encoder. We get the value, which is the change since last year. Every time you do get value on the encoder, it sets it back to 0 again. So it's actually getting the delta between reads that we're doing here. So if I didn't call this function for say 10 seconds, I was just repeatedly rotating that button, it would have a very, very high value. What I do is I compare the last encoder value to the one I've just read with the current, in this case, current volts. And if they're different, I know that the value has been rotated. And so I will adjust it accordingly. A little bit of debug printing here just so that I can have a monitor of what's happening if I'm not looking at the display of the NextGen. I can look at the debug port of the Arduino IDE. And then I repeat the same thing for the amps here, exactly the same. And then I go on to monitoring the two buttons. Then we get to the NextGen functions. So here's the routine for showing the splash. And I'm actually not using the NextGen library specifically here. There is a send command that's built into the library, which all it does is add the FFFFFF to the end of the string and sends it through the serial port to the NextGen. So it's the lowest level of using the library or talking to the NextGen that you can do. So all I do is I set the keypad to my, which is that area that I normally use for the keypad. I set it to the image 4, which is my splash logo. That I then stay there for 4 seconds. I said 5 before, I meant 4. And then I put the image back to invisible, and it just redraws the screen and shows you normal display. So we have the function that updates the displays. The first call updates the set points, which just writes the set point volts and set point amps to the display. So it converts the analog values into ASCII strings and writes it to the display. The next routine writes the actual amps that have been read from the ADC and the actual volts. Then we continue that with the power and the watt-hour measurements. Again, converting from from floating point to ASCII values. The next one is the update trend graph. So this one is basically just saying trend add value 0, 1, 2, and 3. So this is volts, amps, power, and then temperature is trend 3. I have a function here which is called hide keypad. Now with the library with the NextGens, when they built the library, they really built it to support the demonstration HMIs that they had created to show people how to use the NextGens. But at the lowest level, what you normally do is you send out the serial port commands like viz space 255, 0, and then you would have a space, and then you would terminate it with FFFFFF. When we look at what we're doing in the Arduino code here, and we're just calling send command and then saying viz and various other things, keypad, etc., what we end up doing, if I just go to the code for the library, here is the send command. You can see we pass the string in, and all we're doing is serial. If the serial is available, we read data from it just to clear out the buffer. And then all we're doing is we're sending whatever that string was, so viz space 255, 0, and then we're adding a FFFFFF to it, and that's it. So you can do that very, very easily by just using direct serial.print line commands if you wanted to. This just makes it a little bit easier for you, but it's not that complicated even without the library to do things. And what I've done is, because the libraries were written for the demonstrations, they don't include all the functionality I want. For instance, none of the library has the viz statement. Then I've just run through the list of objects that I want to turn on and off, and I've just set the values appropriately in strings here, and I just send it out. Now, if I wanted to minimize how much RAM I'm using, of course, I would put these into flash memory with a progmem statements and things. But right now I got plenty because I'm now using the Arduino Mega. So in this case, this hides the keypad. So what I do here is I actually hide everything with the 255, 0. I then one at a time add back in, or re-enable, the controls that are relevant for the base page. So that's why the 1 at the end of it. 1 turns them on, 0 turns them off. And then a viz 255 says talk to everything. That would imply that you can't have more than 254 objects on any one page, but that's not really too much of a limitation if you think about it. I then have the corresponding show keypad, which turns everything off and then turns on the keypad elements. Now, doing this as opposed to that little insert that I showed you before where it was really, really slow, this to all intents and purposes is instantaneous. So we now go to a next instance function. This one is the initialization. It's the same as the ones that we were using in previous videos where we just set up the callbacks for monitoring. So each of these are effectively the handlers. And doing this makes it very, very easy because you don't have to worry about a case statement that analyzes the string that comes back and then say, if it equals on off, then call this. If it equals this, then call that. And it gets very, very messy that way. This is the cancel one, and all it does is hide the keypad. There's nothing else it needs to do, just hides the keypad. And if we hit the save callback, though, we have a little bit of work to get the value from the screen. So that's the property text.getText. It gets the value from a text box that is sitting right here. This is the Nextian designer that I'm showing you it in. So there's a text box that sits right here, which is when you're typing on here, it actually has the text put into this text box as you're typing. So we get that information. We then convert it. We check whether it's a double. And if it is, it will convert it from ASCII to a floating point, or a double in this case, and store it in the variable number. I then just print it just for the sake of debug information. If it isn't a valid value, then I send out a debug string, and then I also write to the display, and I have a little text area on the display right here, this one that says message area, where I can say invalid value or something like that, and a little message. And I write out the fact that it's an invalid value. So I say volts out of range, not to 30 volts, or I will say amps out of range, not to 5 amps. If it's a good number, hide the keypad and update the set points. Now we've already written to them to the set points up here. See right here, current volts equals number, or current amps equals number, right here. So all we now need to do once we get to the end is we just update the display immediately. It's all about how you do the design anyway. It's up to you. This is just an example. I'm not trying to build an end state product here. I'm trying to help you learn how to do one of your own. You can actually download the designer for these Nextian displays and run it. Even if you don't have a display, you can actually run it with its own scripting right there on your PC without having to have one. So maybe if one of you guys comes up with a really good display for the power supply project, I'll switch my project to use that one instead. Anyway, going down here, we've then just got the last two functions, which are just utility functions, and that's pretty much it. So, as you saw there, the library, all of the library functions, when we looked at that just a moment ago, these functions here, this one is the base level one, but they're all as simple as just taking the command, adding FFFF to the end of it, and that's pretty much it. I was using send commands for a few things because the libraries don't have them, and I wasn't going to get into rewriting the libraries at this point in time. And that's pretty much everything. I don't think that there's anything else that I've missed on this part of it. This is basically looking at getting back into the power supply project, but coupling a couple of other things. I've always said that the next stage of the power supply project is to start automating it. So I want to look at a few different options for controlling it, and one of them is with an Arduino, one of them might be with a TI launchpad, and the third option is with something like either a BeagleBone Black or a Raspberry Pi. With an appropriate display, of course, to go with that. And the first display that I've used, as you've just seen, is the Nextian 7-inch HMI. I will try it with a Raspberry Pi 7-inch display, and if I get a BeagleBone Black, I will try it with that. I'm also going to, just because these 7-inch displays are a little more expensive, we will look at how you would use a much, much smaller display, for instance, maybe a 16-character by 2-row or 20-character by 4-row LCD display, one of the simpler ones. And the nice thing is that most of the functionality that I've just shown you in this Arduino code will not change. All you need to do is update the various places for setting the display values, reading from any event. So in this case, if you were using a 4-line by 20-character display, you'd have a separate numeric keypad. And by keeping the code modular, like the way that I've done here, instead of one massive great big loop, it makes it much easier to handle the differences between different modules. So I'm using a touch screen with a serial interface. If you were using a keyboard matrix, for instance, a 4x4 matrix that just had some basic numerics on it, then you'd be scanning that through some of the I/O pins, and the routine would change, but at the end of the day, what came out of that routine would be exactly the same. So we will probably be revisiting some of the example Arduino code that I've done in my earlier tutorials that are on my YouTube channel right now. In the case of the Arduino Mega, we have a lot of memory. We've got 256K of flash, we've got 8K of RAM, and we've got a whole boatload of I/O too. So it's more than capable of running the power supply if that's what I end up doing. Now, because I want to add SCPI and other networking features and things like that to it as well, and potentially have it also running a battery analyzer, DC load, a constant current source, and things like that, then I may ultimately end up using a Raspberry Pi or a BeagleBone Black, something with a higher level OS, and then use I2C or SPI buses to talk to various chips that would communicate with the hardware. And the basic principles are exactly the same, and we're going to be coding it probably in C or in something similar anyway, even if I use a Raspberry Pi or a BeagleBone Black. For now, though, I'm going to be just doing the first parts of this with an Arduino. They're very familiar to most people, as mind you, so is the Raspberry Pis. But I want to spread the knowledge around a little bit to a lot of my subscribers and viewers so that you can apply it to your own applications. So if today I'm using the Arduino and maybe in the next video I'm doing something similar but with a Raspberry Pi, don't worry, I will be doing more with each of those, and I hope that what you get out of this is a sense of how you would take the various parts of this modular bench power supply system and apply it to your own project. I'm not trying to give you a complete end solution here, although it may look like it sometime. Anyway, I hope you like this, and that's all I'm going to do for this video, and we will see you on the next one, hopefully in a week or two's time. The next iteration of the power supply project will come out, and we will continue. We'll have some actual analog to digital, digital analog converters, and hopefully be driving the real outputs of the bench prototype power supply.